This is my supercut on how to draw Lewis structures. It takes my best content and puts it all in one video. We'll start with the basics and then work our way up to things like formal charge, resonance, or even how to draw Lewis structures for ionic compounds. This first video, it's a bit old. The sound quality isn't that great, but it's extremely effective. Let's get started.
At the end of this video, you'll be a pro at drawing the basic Lewis structures. There really are only 5 main steps that you need to know. Let's get started. Step 1. Find the total number of valence electrons for the molecule you're drawing the Lewis structure for. Let's try one. We'll use the periodic table to figure out how many valence electrons each element has. Hydrogen is in group 1 on the periodic table, so it has 1 valence electron, but the subscript tells us that we have 2 hydrogens. So we'll need to multiply that by 2. Oxygen is in group 6 or 16. It has 6 valence electrons, and when we add that up, 2 plus 6, we get a total of 8 valence electrons for H2O. Remember, valence electrons are the outer shell electrons. They're the ones that form chemical bonds and interact with the world around them. Let's try one more, cyanide. For cyanide, we can look on the periodic table again. Carbon has 4 valence electrons, and nitrogen has 5. The trick for this one is, though, it's a negative ion. This negative sign right here tells you that there's going to be 1 extra valence electron. So 4 plus 5 plus 1, 10 valence electrons for the cyanide ion. Step 2. Put the least electronegative atom in the center. So how do you know it's the least electronegative atom? Just remember that fluorine is the most electronegative, followed by oxygen. So as you move away from fluorine and oxygen, atoms become less electronegative. That means those atoms will go at the center. Let's see how it works. When I draw the Lewis structure for something like NO2, I can see that nitrogen is further away from fluorine than oxygen. That means when I draw my Lewis structure, I'll put nitrogen at the center and oxygens on the outside. For something like PCl3, I can see that phosphorus is further away from the fluorine than the chlorine atom. So I'll put phosphorus at the center and the chlorines on the outside, like this. Some Lewis structures, like HCl, only have 2 atoms. In that case, you don't have to worry about it because there's no center. An important note, hydrogen always goes on the outside of Lewis structures. Always. Seriously. Let's look at HCl again. We know it has 8 valence electrons, and we'll put the first 2 in our structure between the H and Cl to form a chemical bond. That's important. By putting those 2 electrons there, we're showing that the hydrogen and the chlorine are chemically bonded now. Step 4. Complete the octets on the outside atoms. Octet means 8. For HCl, we have a total of 8 valence electrons, 1 for the hydrogen, 7 for the chlorine. So we've used 2 already to form the chemical bond. For the chlorine, we'll put 4, 6, and then 8. We've used all the valence electrons, and we've completed the octet for chlorine. It has 8 valence electrons. For basic Lewis structures, the big exception is going to be hydrogen. It only needs 2 valence electrons for a full outer shell. So hydrogen has a full outer shell with 2 valence electrons. The chlorine, its octet is full with 8, and we've used only the 8 valence electrons that we have for the HCl molecule. We're done with this structure. There's one more rule that we need to look at. It doesn't apply to HCl, and actually it doesn't apply to a lot of molecules. But what happens when you've used all your valence electrons and you still haven't completed the octets for each atom in the molecule? That's step 5. So sometimes you run out of valence electrons and still haven't filled the octets. Hey, it happens, right? So in step 5, what we're going to do is if we run out of valence electrons, we'll move some of the valence electrons from the outside to the inside and share them and form double and triple bonds. Here's how it works. So for O2, oxygen, if I follow all the rules, I count the valence electrons, I have 12, and if I put a bond between the atoms and then fill the outer shell, I end up with the situation where I have an octet for this oxygen, it has 8, but this oxygen only has 6 valence electrons. it doesn't have an octet and I don't have any more valence electrons. To solve the problem, I can take these valence electrons right here and move them to the center to share them and form a double bond between the two oxygen atoms. I'm still only using 12 valence electrons, but now this oxygen has 2, 4, 6, 8 valence electrons, and this oxygen has 2, 4, 6, 8 valence electrons. So by sharing those valence electrons, I can get the octet on each of the oxygens and still use the 12 valence electrons that I had for the O2 molecule. If I wanted, I could replace these right here with 2 lines to show the double bond, where each line represents a pair of electrons. For Lewis structures like N2, I would even use a triple bond to achieve octets. So how do you get good at drawing Lewis structures?
So now that you have the basics, we're going to practice. Practice is the key to success here. They'll start out easy and get harder as we go. So if they're too easy at first, skip ahead. Try some of the harder ones. Once you're done with the practice, we'll look at formal charge, we'll look at resonance, and then even drawing Lewis structures for ionic compounds. So here is the practice video. In this video, I'll explain how to do these 9 Lewis structures. The way to use the video: do one of the Lewis structures and check your work. When you're done, go back and do some other ones. They'll get harder as you go on, and that's to help you learn more complex Lewis structures. Just a quick note, whenever you have a pair of electrons like this, that's called a single bond. And we can write a single bond also is just by putting a line like this. So in our NH3 Lewis structure here, we can replace the bonds, these are the pairs of electrons between 2 atoms, with single lines. And that'll mean the same thing. It's the same Lewis structure, just a different representation. We'll start with the Lewis structure for OF2. First, we find the valence electrons. So oxygen is in group 16, sometimes called 6A. It has 6 valence electrons plus fluorine, which has 7, but we have the 2 fluorine, so we'll multiply that by 2, and that gives us 6 plus 14, a total of 20 valence electrons. Next, we'll put the least electronegative atom in the center of the Lewis structure. That's going to be our oxygen, and then on either side, let's put the fluorine atoms. We'll place a pair of electrons between the fluorine and the oxygen here to form a chemical bond, and then over here. Once we've done that, we'll complete the octets around the fluorine atom. So we'll want to have 8 valence electrons around each fluorine atom. So now the fluorines have 8 valence electrons. They have an octet. We've used 16. That means we have 4 more valence electrons. We'll move back now to that central atom. We'll put 2 valence electrons here, and then 2 here. And we've used all 20 valence electrons, and each of the atoms in this Lewis structure has an octet. So we're done with the Lewis structure for OF2. For the CH4 Lewis structure, let's find the number of valence electrons. Carbon is in group 14, sometimes called 4A. It has 4 valence electrons. Hydrogen has 1 valence electron, but we have these 4 hydrogens, so let's multiply this by 4. If we add that up, 4 plus 4 equals 8. So we have 8 valence electrons for the CH4 Lewis structure. We'll put the carbon in the center. Hydrogen atoms always go on the outside. So we'll put the carbon in the center, and then we'll put the 4 hydrogen atoms around it. Next, we'll put a pair of electrons between each of the atoms to form a chemical bond. So we'll put 2 here. At this point, the carbon has an octet. We've used 2, 4, 6, 8. We've used all our valence electrons, and the hydrogens, they each have 2. This is an important rule. Hydrogens only need 2 valence electrons to have a full outer shell. So the carbon has an octet, the hydrogens each have 2. We're done with this Lewis structure. H2 is probably about the simplest Lewis structure we can draw. So if we count the valence electrons up, hydrogen is in group 1. It has 1 valence electron, but we have the 2 hydrogens. We multiply those together. 1 times 2 is 2. So we have a total of 2 valence electrons. So we'll put our 2 hydrogen atoms right here next to each other, and then we're going to move 2 valence electrons between them to form a chemical bond. And when we do that, we've used both of the valence electrons. Hydrogen has 2. We said that hydrogen is an exception. It only needs 2. And that's the Lewis structure for H2, hydrogen gas. CO2, carbon dioxide, is a little bit more of a complicated Lewis structure, but it's not too bad. Let's count the valence electrons. We have 4 for carbon. Oxygen has 6, but we have these 2 oxygens. And that gives us a total of 4 plus 12, 16 valence electrons. We'll put the least electronegative atom in the center of the Lewis structure, that's the carbon, and then we'll put an oxygen on either side. Next, we'll move electrons to the center to form the chemical bonds. Once we form those chemical bonds, we'll complete the octet around the oxygen atoms. We have a total of 16 valence electrons. And now we've completed the octets on the oxygen atoms. But we've used 16 valence electrons, and we don't have any more. The carbon in the center, though, it only has 4 valence electrons around it. It doesn't have an octet. To solve this problem, we can move valence electrons from the oxygen atom to the center between the carbon and the oxygen so that they share valence electrons. So when we do that, the oxygen atom, it still has 8 valence electrons, but now the carbon atom has 6. We're almost there. Let's take 2 from this oxygen, move them to the center. Now, this oxygen here still has 8. This oxygen has 8. And the carbon in the center has 8 valence electrons, and we're using all 16 of the valence electrons here, no more. So this is the Lewis structure for CO2. We call this a double bond. For the BH3 Lewis structure, boron has 3 valence electrons. It's in group 13, sometimes called 3A. Hydrogen has 1, and we have 3 hydrogens. So we have 3 plus 3, total of 6 valence electrons for the BH3 Lewis structure. Since hydrogen always goes on the outside, we'll put the boron in the center, and then we'll put the 3 hydrogens around it. We'll start by putting pairs of electrons between atoms to form chemical bonds. We've created the chemical bonds, but we've used 2, 4, 6 valence electrons, and we only have 6 valence electrons. So how do we complete the octet for the BH3 Lewis structure? It turns out that with Lewis structure there are quite a few exceptions. The octet rule is a very general rule. It works a lot of the time, but not all the time. So for boron, it's one of the exceptions. Boron only needs 6 valence electrons. We'll see more of these exceptions later on. O3 is also called ozone. We have 6 valence electrons for oxygen, and we have the 3 oxygens for a total of 18 valence electrons for this Lewis structure. We'll write the 3 oxygen atoms, and we'll just put them next to each other. So 1, 2, 3. Next, we'll put electrons between the oxygen atoms to form the chemical bonds. We've used 2, we have 16 more. Let's complete the octets on the oxygens on the outside. So we've used 16 valence electrons. We have 2 more, and we'll put those on the central oxygen. And we have octets on the outside, on the oxygens on the outside, but that central oxygen, it only has 6 valence electrons. So much like we did with carbon dioxide, we can move a pair of electrons to the center. When we do that, these 2 oxygens are sharing those electrons. So this oxygen has 8, the central oxygen has 8, and then this oxygen over here on the left also has 8. When we have Lewis structures like this, there's another way we could draw it. You can see the only difference here is we have the double bond here, and on this one we have the double bond on this side. These are called resonance structures. Often when we draw Lewis structures, you're asked to draw the resonance structures. Those are the different ways you can draw the Lewis structure. Here we have a double bond on the right, and here we have it on the left. We have something a bit odd with this Lewis structure, and that's that plus sign up there. Whenever you have a plus sign, it means the ion, the compound, it's positive. And to be positive, it lost an electron. So when we write up the number of valence electrons, nitrogen has 5 plus the 4 oxygens. We need to subtract 1 valence electron because the plus means we've lost one. If this were a negative sign, it would mean we gained one. So 5 plus 4 is 9, minus 1. We have a total of 8 valence electrons for this NH4 plus ion. We'll put the N in the center, hydrogen, always on the outside, and then we'll put the 4 hydrogens around it. We have a total of 8 valence electrons. Let's put a pair of electrons between each of the atoms, form a chemical bond. There. So we've used all 8 valence electrons. The nitrogen, it has a full outer shell, has an octet, and the hydrogens, they only need 2. They all have full outer shells. That's the Lewis structure for NH4+. It's called the ammonium ion. For SO4 the sulfate ion, sulfur has 6 valence electrons. Oxygen also has 6. We have 4 oxygens. And this 2- up here, that means we have an extra 2 valence electrons. So we'll add those right there. We have 6 plus 24, that's 30, plus 2 gives us 32 valence electrons for this Lewis structure. We'll start by putting the least electronegative atom in the center, that's the sulfur, and then we'll put the 4 oxygens around it. We have 32 valence electrons. We'll put 2 between each of the atoms to form the chemical bonds. Then we'll go around and complete the octets on the oxygen atoms. Whew, that was a lot of electrons. If we add all of these electrons up, you'll see that we've used 32 valence electrons. The sulfur has an octet, as do all of the oxygen atoms. It looks like we're done with this Lewis structure. Everything has octets. We've used all the valence electrons. It's all good, right? However, if you're in a more advanced chemistry class, you'll learn that sulfur and other atoms in the periodic table that are in period 3 or below, they can have what's called an expanded octet. An expanded octet means that the central atom there would have more than 8 valence electrons. The way we tell is we check the formal charges. I'm not going to do that right here, but I'll show you what the correct structure looks like after we find the best formal charges. This is actually the best Lewis structure for the sulfate ion. All of the formal charges are 0. Each of the oxygen atoms has 8 valence electrons. The central sulfur has 2, 4, 6, 8, 10, 12, but that's okay. It can do that because it's in period 3 on the periodic table or below. It can have that expanded octet. So this is the best Lewis structure for SO4 the sulfate ion. We should also put brackets around this with that 2- to show that it's an ion. And there you have it, the Lewis structure for SO4 the sulfate ion. For phosphate, we have 32 valence electrons. It's likely when you do the Lewis structure, you'll come up with something initially that looks like this. And that makes a lot of sense. We've used all 32 valence electrons. Each of the atoms has an octet. Looks like a pretty good Lewis structure. Again, when we have atoms that are in period 3 or below on the periodic table, especially things like sulfur and phosphorus, we should check the formal charges to make sure that this is the best or the most favorable Lewis structure. I won't do that here. There's a link to a fuller video you can watch. But when we do it, here's what we end up with. The only difference is that we have a double bond here between the phosphorus and the oxygen. Everything else stays a single bond. We still use the 32 valence electrons. So checking the formal charges is a very good idea if you're in an advanced chemistry class. One last thing, we should put brackets around this since it is an ion, and then we'll write the 3- right up here. And that's the Lewis structure for PO4 3-, the phosphate ion. Yet another video with awesome sound quality for you. This video is on how to find formal charge, and we use that to tell between 2 different Lewis structures that both follow the rules, but how to figure out which one is the best Lewis structure. So watch the video, do the practice, and then after that we'll move on to resonance and drawing Lewis structures for ionic compounds. Off you pop.
So formal charges allow us to figure out which is going to be the best structure for a chemical compound. And by best, I mean the one that's most likely to exist in the real world. So let's start with a simple one. Let's look at CH4, methane. To calculate formal charges, we do that for each atom. So let's take a look at the carbon first. Carbon on the periodic table is in group 4 or 14, 4 valence electrons, minus non-bonding. These are the ones that aren't formed in chemical bonds. All of these electrons for carbon, they're bonded, so we don't have any non-bonding. And then bonding electrons, we have all of these right here. So we have a total of 8 bonding valence electrons. Divide that by 2. 4 minus 0 minus 4 is 0. So we can write the formal charge for carbon and put it right here in the middle as 0. So now let's try the formal charge for hydrogen. Since all the hydrogens are the same, they're symmetrical, we only need to do 1. So valence electrons, hydrogen's in group 1, so 1 valence electron. Non-bonding, these guys are all bonded, so 0, and then the 2 bonding, valence electrons, divided by 2. 1 minus 1 equals 0. So the formal charge for hydrogen is 0, and that's the same for all the hydrogens since it's symmetrical. So that's methane. So we've calculated the formal charges for methane. Not too bad if you can remember the formula. So often you'll have more than one possible Lewis structure, and this happens quite frequently when you have something like sulfur in period 3, row 3 of the periodic table, or phosphorus in the same period. They can have more than 8 valence electrons, and that opens up some possibilities. So you want to check the formal charges, especially when you see sulfur or phosphorus. So let's try it. We'll do this oxygen first, and oxygen is in group 6, so it has 6 valence electrons. Non-bonding, that's these ones on the outside, has 6 of those. And then bonding, we have a bond right there, 2 divided by 2, so 6 minus 1 is minus 1. The formal charge on that oxygen is minus 1. For the sulfur, right here, we have group 6, non-bonding, that's these here, and then bonding, these and these are forming bonds, so we have 6 over 2, and 6 minus 2 minus 3 equals a positive 1. So this is going to have a formal charge of plus 1. For the last oxygen, we have 6 valence electrons, non-bonding, these here and here, so 4. And then bonding, 4 of those, divided by 2. 6 minus 4 minus 2 is 0. That has a formal charge of 0. Let's try this molecule over here. So we're going to do this oxygen. We have 6 minus 4, and then these are our bonding, so 4 over 2. That equals 0. Formal charge of 0. For the sulfur, we have 6 minus non-bonding minus the bonding, so we have 8 over 2 there, and that equals 6 minus 2 minus 4. We have 0 again, formal charge of 0. Finally, the last oxygen here, we have 6 minus 4 non-bonding. We have 4 bonding over 2, 6 minus 4 minus 2, a 0 again. Formal charge of 0. So when we look at these structures, we want to choose the one that has the formal charges close to 0. And in this case, that's right here. This is the structure that has the formal charges closest to 0, and therefore that's going to make it the most appropriate or the best Lewis structure, the one that we're likely to find in the real world. You've got your equation for figuring out formal charges. You can calculate them for each atom and then compare different structures. It's a little bit confusing at first, but with practice, it gets pretty easy.
Formal charge, it's a bit of work, but it's a powerful concept. In this video, we'll look at 4 different compounds, calculate the formal charges on each atom, and then use that information to decide which molecule is most favorable, or the best molecule. If it's too easy, move ahead. We're going to look at resonance next, which is related to formal charge, and then we'll look at drawing Lewis structures for ionic compounds. Give it a try. To practice calculating formal charge, we have 4 different compounds, and they each kind of show a different aspect of things you'll run across when you calculate formal charge. There's also a description of the formal charge equation, and it shows you how that's set up and what the different terms mean. The way to use the video, work out the problem, say H2O, find the formal charges for each atom, and then below, you'll see that there's a time. That's the time in the video that you should go to, and then check your work. Watch the explanation if you're having problems, and then move on to the next one. This is Dr. B, and enjoy the video. I won't go into the theory of formal charges a lot here, other than to say that when we draw our Lewis structures, sometimes we have Lewis structures that we can draw 2 different ways and still obey the octet rule or still have a valid Lewis structure. What the formal charges do is they tell us a reasonably reliable way to tell what's the most favorable or the most likely Lewis structure that we'll see in that molecule in the real world. And the best Lewis structure from the formal charge standpoint is one that has formal charges closest to 0. 0 is even better. So this is the equation we're using for formal charges. So in the equation, we calculate formal charge for individual elements. So for instance, let's look at the oxygen up here. The number of valence electrons for oxygen is 6. It's in group 16 or 6A on the periodic table, so we know oxygen has 6 valence electrons. For the unbonded electrons, these are the ones not involved in chemical bonds. So when we look at the H2O, we have these electrons here, this pair and this pair. They're not bonded to another element. They're called unbonded. So we have 1, 2, 3, 4 unbonded electrons around that oxygen atom. Finally, we're going to subtract 1/2 of the bonded electrons. These are the electrons between elements. So for the oxygen, again, we have the 2 here. This line represents a pair or 2 electrons that are shared. So we have the 2 here and the 2 over here. So we have 4 bonded electrons, and then we would take half of that. So that's the equation that we'll be using to calculate formal charge. So pause and figure out the number of valence electrons, then the bonded and unbonded for the oxygen, and then for the carbon in this CO2 molecule. So let's take a look at the oxygen first. Both of the oxygens are the same, so we only need to do one of them. Oxygen is in group 16, sometimes called 6A on the periodic table. It has 6 valence electrons. It has a total of 4 unbonded valence electrons, and then a total of 4 bonded valence electrons. And that's because each one of those lines represents a pair of electrons, and we have 2 lines. So 2 plus 2 equals 4. For the central carbon, carbon's in group 14, sometimes called 4A. It has 4 valence electrons. It has no unbonded valence electrons. They're all involved in bonds between the carbon and the oxygen atoms. And then finally, bonded valence electrons. We can see there are 1, 2, 3, 4 bonds. Each one has 2 electrons, has a pair. So 4 times 2, we have a total of 8 bonded valence electrons for carbon. So use this information to calculate formal charge on the compounds in the practice problems. We'll start with H2O, water. It's a little bit simple, but it's a good one to start with. So let's calculate the formal charge here for this hydrogen. So I have my hydrogen, and the number of valence electrons for hydrogen, it's in group 1. It has 1 valence electron. Hydrogen will always have 1 valence electron. We'll subtract the unbonded electrons around the hydrogen, and all of the electrons for the hydrogen, they're involved in this chemical bond. So unbonded electrons, there are none. Then we're going to take 1/2 of the bonded electrons. That's this right here. This is what's connecting the oxygen and the hydrogen. It's the chemical bond. The line represents a pair of valence electrons, so we have 2. And when we do the math, 1 minus 0 minus 1, we have a formal charge of 0. And we can put that up here just like this. And since this hydrogen is exactly the same as this one, we can put the formal charge for that one. We don't have to recalculate. For the oxygen, oxygen is in group 16, sometimes called 6A. It has 6 valence electrons minus the unbonded valence electrons. We have 2 here and 2 here. So we have a total of 4 unbonded valence electrons minus the bonded electrons. So we have the pair here. There's 2 plus these 2. That's 4. And 6 minus 4 is 2. Minus 4 over 2, that's also 0. So we can put a 0 up here for the oxygen. It's not surprising that the formal charges are 0. It's a fairly simple atom. But it's a good example, and it'll help us as we do more complex problems. For CO2, let's start with this oxygen right here. So oxygen, and oxygen has 6 valence electrons. It's in group 16, 6A on the periodic table, minus unbonded electrons. We have 2 here and 2 here, so 4 unbonded valence electrons. Subtracting from that the bonded electrons, 2 plus 2 is 4 of the bonded electrons, and we're dividing that by 2. When we add this up, we have 6 minus 4, that's 2, minus 4 over 2. So the formal charge on the oxygen is 0, and we can just write a little 0 up here, and we can do the same for this oxygen since it's symmetrical. It looks exactly the same. For the carbon here in the center, carbon has 4 valence electrons. Unbonded, there are none. All of the electrons are involved in these bonds here with the oxygen. And then bonded electrons, we have 2, 4, 6, 8. So 8 divided by 2, and 4 minus 0 minus essentially 4 is 0. So the formal charge on the central carbon there that's 0 as well. So we have our Lewis structure here for NO3-, the nitrate ion. Do note there are resonance structures. You could put the double bond here, or you could put it here. But really the way we'd go about calculating formal charges, it's the same. So let's start out by calculating the formal charge of this oxygen here with the single bond. So we have our oxygen, which has 6 valence electrons, unbonded, 2, 4, 6, minus the 1/2 of the bonded. And we have just this pair of electrons here, 2 over 2. So 6 minus 6 minus 2 over 2. We have a -1 formal charge on this oxygen right here. And since this oxygen is the same as this one, let's put a -1 there as well. For the oxygen with the double bond, that equals 6 valence electrons minus unbonded, just the 2 plus 2, 4, minus 1/2 of the bonded. And this oxygen has 2, 4 bonded valence electrons. And 6 minus 4 minus 4 over 2, that gives us 0. So we'll put our 0 right up here. For the nitrogen there in the center, nitrogen equals 5 valence electrons minus unbonded. All of these electrons are involved in chemical bonds, so we have 0 for unbonded, minus 1/2 of the bonded, 2, 4, 6, 8. So that's 8. 5 minus 0 minus 4, that gives us a +1 on that nitrogen. So we'll put a +1 up here. So for these formal charges, if you add them up, -1 and a +1 and a -1, that gives us an overall charge on this entire molecule of -1. And that makes sense because it has a negative charge. So those are the formal charges for NO3-, the nitrate ion. For XeO3, xenon trioxide, I've drawn 2 Lewis structures, and both of these Lewis structures are correct. They follow the rules for writing Lewis structures. We have octets for the oxygen atoms on both structures. Xenon, it's below period 3 on the periodic table. It's an exception to the octet rule. You can have an expanded octet, so it's okay as well. And the only difference is I have 2 double bonds here, and on this side I have a single bond and a triple bond. So I'm using the same number of valence electrons. The oxygens are obeying the octet rule, so they're valid Lewis structures. So which one's the best? And that's what the formal charges are going to tell us. So let's find the formal charges. We'll start over here and work with this oxygen first. So for this oxygen, 6 valence electrons for oxygen, minus the unbonded, 2, 4 unbonded, and then minus 1/2 of the bonded electrons. So we have 2 bonds, 2 electrons in each, 4 unbonded electrons. So 6 minus 4 minus 2 gives us 0. So the formal charge on this oxygen right here with the double bond, that's 0. And in fact, all of these here are the same, so they're going to be 0. For the xenon in the center, xenon is in group 18, 8A. It's a noble gas. It has 8 valence electrons. Then unbonded, there are 2 of them up there. And then bonded, we're going to divide that by 2. We have 2, 4, 6, 8, 10, 12 bonded valence electrons. So 8 minus 2 is 6, minus 12 over 2. That gives us 0 as well. So the formal charge on the xenon here is 0. So this looks like a pretty good structure because all the formal charges are 0. If we calculate the formal charges for this molecule right here, this is what we end up with. You can see that our formal charges are not as close to 0. These are all 0. Here we have a -1, and then we have this +1 on an oxygen, which is kind of odd because oxygen is very electronegative. So this structure here is going to be less likely. This is the most favorable or best Lewis structure for XeO3. Wow, so you've made it to the end of the video here, and hopefully now you're pretty good at calculating formal charges. Formal charges are really useful in chemistry because they let us quickly kind of figure out what the charge density, where the charge is on a molecule. And if we know that, that tells us something about the physical properties and how it'll bond to other molecules. That's pretty important when you're looking at things like drug chemistry or materials science. This is Dr. B with a lot of practice on formal charges, and thanks for watching.
So now you're good at formal charges. One idea that you need to add is resonance. So if you take a look at this, right here are 3 ways we can draw the carbonate ion. That arrow, it doesn't mean they're switching back and forth between those ways. What it means is the actual molecule's an average of those structures. So watch the next 2 videos, see how we do these resonance structures, and then we'll wrap up with this supercut for Lewis structures
by doing some ionic compounds, drawing those Lewis structures. On to the next video. To draw the resonance structures for CO3 2-, the carbonate ion, we start with a valid Lewis structure. So we can see each of the atoms, they have an octet here, and we're using only the valence electrons that we have for this structure. We could also add the formal charges on the oxygen here with the single bond, that's -1, and this oxygen here with the single bond has a formal charge of -1. Those both add up to -2. That makes sense. So this is one Lewis structure that we could draw. When we talk about resonance, we often talk about pushing electrons to draw different resonance structures. So that means I could move these valence electrons right here from the double bond out here, and then these electrons on the single bond, I could make a double bond here. That would look like this. So we'll move these two out here like this. Then we'll move these two right here to form the double bond. The formal charges, they'll still be on the oxygens with the single bond, so these two here. When we did this, note that we maintained the same number of valence electrons in each of these structures, and that the atoms, they didn't move, only the electrons moved. Let's draw another one. Let's push these electrons up here. Now we have a single bond, and then we can push these electrons to form a double bond. Again, our formal charges, those will be on the oxygens with the single bonds. So this is another resonance structure we can draw for the carbonate ion. We should put these arrows between resonance structures, as is convention, and we should put brackets around the resonance structures. So these are the three ways we could draw the resonance structures for CO3. Note that we have the same number of valence electrons in each structure. Everything has an octet, they're valid Lewis structures, and we didn't move any atoms, we only moved electrons. Understand that these arrows, they don't mean that we're switching back and forth. These are all just three different ways to look at the same structure for the carbonate ion. In fact, the actual structure is an average of the three. That might look like this. You can see with this representation, we really just have an average of these three here. This is Dr. B with the three equivalent resonance structures for CO3 2-, and thanks for watching. In this video, we'll draw the resonance structures for N2O. This is dinitrogen monoxide. It's also called nitrous oxide. So let's first count up the electrons, then draw some resonance structures. Nitrogen is in group 15, sometimes called 5A. 5 valence electrons. We have 2 nitrogen atoms. Oxygen's in group 16, so we have 6. So we have a total of 16 valence electrons for this N2O Lewis structure. So nitrogen is less electronegative. So we're going to put the nitrogen in the center, the oxygen on this side here, and then we'll put the other nitrogen over here. So this is our skeleton for our Lewis structure. Let's put electrons between atoms. That'll form our chemical bond here. So we've used up 2. We have 12 more. Complete the octet on the oxygen. We've used 10, so let's complete the octet on this nitrogen. 10, 12, 14, and then 16. But you can see the central nitrogen does not have an octet. So we can move 2 here. That gets us closer. We still have an octet here. We have 6. Let's move 2 here. And at this point, we have a valid Lewis structure. If we calculate the formal charges for each atom, this is what we get. So this is pretty good. We'd rather have everything 0, but this is close. There is another way to draw this. It would be a resonance structure of N2O. So let's do that. We could have a triple bond here and then a single bond on the oxygen. Let's try that. So we can move this over here, and then we can move this pair to form a triple bond. So this is also a valid Lewis structure. We have 8 valence electrons here, 8 here, and 8 here. We're using 16. Let's write the formal charges in for this structure. So it doesn't look that different. We have a +1 and a -1, but there is a key difference, and that's that oxygen is more electronegative. So when we have formal charges, it's best to have the negative formal charge on the more electronegative element. So here we have oxygen, it's more electronegative. It has the negative formal charge. Over here, we have the negative formal charge on the nitrogen, the oxygen 0. So this structure is actually a more favorable or a more stable resonance structure of N2O. There's one more we can draw. That'll look like this. So with this structure, we do have an octet for the nitrogens and the oxygen, but we have this -2 formal charge on this nitrogen. The oxygen has a positive formal charge. This really isn't a very stable structure. So there are two major resonance structures for N2O, and we'll often put this little arrow between them to show that they're resonance structures. It doesn't mean they're switching back and forth, it just means they're an average of these structures. So we only would have one structure. In reality, that would just be an average of these. And most of it would be this resonance structure here, because the formal charges make the most sense. The negatives on the oxygen, and then we have all the octets satisfied. So this is the major resonance structure. This would be a minor structure, and this would be a very, very minor structure, if even at all. This is Dr. B with the resonance structures for N2O, nitrous oxide. Thanks for watching. The last video in our supercut here is how to draw Lewis structures for ionic compounds. You see, in the covalent compounds or the molecular compounds, electrons are shared. But when you have that ionic compound, they actually get transferred. So you have to draw it a little bit differently. So give this a try, and once you're done, you're going to be a pro at drawing Lewis structures. In this video, we'll learn to draw Lewis dot structures for ionic compounds. Ionic compounds are made up of a metal and a nonmetal, or a metal and a group of nonmetals. So use the color-coded periodic table here to identify which of these three are ionic compounds. And be careful, because hydrogen is a nonmetal, even though it's grouped on the metal side of the periodic table. For CaCl2, calcium, that's a metal. Chlorine, that's a nonmetal. So this is an ionic compound. For NaNO3, Na, sodium, that is a metal, and then we have N and O, nitrogen and oxygen, which are both nonmetals. Metal in a group of nonmetals, that's ionic. And finally, H2O, water. Hydrogen, that's the one we have to watch out for. It's a nonmetal. Oxygen is a nonmetal. So that's not an ionic compound. That's a covalent compound. It's important to note that in ionic compounds, the metal, that will transfer those valence electrons to the nonmetal. And this influences how we write Lewis structures for ionic compounds. So let's write us some Lewis structures. We'll start with the iconic ionic, NaCl. To write the Lewis structure for sodium chloride, NaCl, we first look at the periodic table. We see sodium, that's a metal. Chlorine is a nonmetal, so we have an ionic compound. Let's write Na and then Cl. Next, we need to figure out how many valence electrons each of these elements has. So we go to the periodic table, and we can see that sodium, that's in group 1, and those elements have one valence electron. So let's put that out there. Chlorine, that's in group 17, sometimes called 7a. It has 7 valence electrons. We said that in ionic compounds, the metal will transfer its valence electrons to the nonmetal. So we have the 1 valence electron here, and we'll transfer that to the chlorine. And when we do that, the chlorine now has 8 valence electrons. It has a full outer shell, called an octet, which is very stable. The sodium doesn't seem to have any valence electrons, but the shell underneath is full, so it too has a full outer shell. Because sodium lost a valence electron, and electrons are negative, it's become positive. So we'll put a plus out here, which stands for 1 plus. The chlorine, it gained that electron. Electrons are negative. The chlorine's now negative. By convention, we should put brackets around the negative ion. You'll also sometimes see brackets around the positive ion as well. And that makes this the Lewis structure for NaCl, sodium chloride. Understand that what we drew, the Lewis structure for NaCl, is actually what's called a formula unit. When you have a crystal, that's made up of a bunch of these formula units in a regularly repeating pattern. So you can see the crystal here on the right with its repeating patterns of NaCl. But by writing the Lewis structure for the formula unit, that helps us understand the behavior of those valence electrons. Okay, your turn. Pause and write the Lewis structure for CaCl2, calcium chloride. We have our calcium, and then we have 2 chlorines. I'll put 1 on each side. We know that calcium has 2 valence electrons because it's in group 2 on the periodic table. And then chlorine, just like before, group 17, sometimes called 7A, 7 valence electrons. The metal will transfer electrons to the nonmetals, so one will go here to give an octet to this chlorine, the other one goes here. And now, since the calcium has lost 2 valence electrons, it has a 2+ charge. The chlorines, they've each gained 1 electron. They become a 1 negative. We put brackets around the chlorines, and that makes this the Lewis structure for CaCl2. Let's do one more. NaNO3, sodium nitrate. We have sodium, that's a metal, and then nitrogen and oxygen, those are both nonmetals, so this is an ionic compound. Let's write the Na. And then NO3, it's called a nitrate, and when you see this ATE at the end, you know that's a polyatomic ion. So it's going to stick together. The nitrogens and oxygens, they're tightly bound together. So we'll write NO3. And sodium, because it's in group 1, it has 1 valence electron. But then we have this NO3 polyatomic ion, and that's a little bit challenging. Because the N and the O, those are nonmetals, and it's tightly bound together, we need to do a Lewis structure just for NO3, the nitrate ion. So we'll replace the NO3 with a Lewis structure, and you can check in the description for the video for a link on how to draw the nitrate Lewis structure. So here we have the Lewis structure for NO3, and we said that the sodium, being the metal, will transfer that valence electron to the nonmetals. Since it's lost the electron, it becomes a 1+, and the NO3 that gained it, that becomes a 1-. We put brackets around the anion, the negative ion, and that makes this the Lewis structure for NaNO3, sodium nitrate. There are links to more practice in the description for this video, and you should make sure that you can draw the Lewis structures for compounds made of 2 nonmetals, covalent compounds. So that's it. If you made it this far, you're amazing. You should be a pro at writing Lewis structures. This is Dr. B with my Supercut for drawing Lewis structures, and as always, thanks for watching.